Hi there, folks. So that's a continuation of the class on calculating the electric field. Now we're going to do electric field of continuous charge distribution. First, what I'm going to do, I'm going to give you a qualitative idea how we calculate that, and then you're going to attack some specific problems that will allow you to solve different distributions of electric charges, for the electric field of different distributions of electric charges. Okay, so the generic way of treating this problem, the generic way of presenting this problem, is considering the most arbitrary distribution of electric charges. Let us say we have a positive charge distribution. It's not a point charge. It's just this form 3D object that's somewhere in space, okay, and we want to calculate the electric field at this point right here in space. There's no other electric charge here. There's just an empty space in which I want to find out the electric field around this object, this charged object. We started by visualizing a infinitesimal charge in that object. At that infinitesimal charge at that position has the following position vector from the charge to the point, right? So we want to calculate the electric field at this point here. So we have to be aware that there is a vector position from the infinitesimal charge distribution to that spot. And then that infinitesimal charge distribution, the dq1, has this contribution to the net electric field at this spot. Okay? And then another infinitesimal charge distribution, dq2, also has a vector position from the charge to the point where we are calculating the electric field. This infinitesimal charge distribution is going to contribute another infinitesimal electric field at that point. Okay, and so on. Here is going to be a dq3 charge. It will also contribute an electric field. So the idea here is to pick up every possible electric charges that you have, infinitesimal electric charges that you have in this volume, visualize the electric field, and then sum the contributions of each one, like we did to the point charges. Okay, so that's the first thing that you have to keep in mind. So the trick here is to integrate over all, to sum or to integrate over all those possible infinitesimal charges, find out the infinitesimal electric field contribution at this point, and sum them all. Okay? That's the key idea behind that, behind the solution of electric field. You saw it in a graphical sense, how the net electric field can be calculated, right? Mathematically speaking, I'm going to be very explicit about that. How do you calculate that? You, in a mathematical sense, you write down the electric field, the infinitesimal electric field of each of those infinitesimal charge contributions, right? And you sum for the contribution of each one. Okay, and that's the equation that you use, the infinitesimal electric field, k dq over r square r hat. That's the first numeric problem we're going to solve, okay? Is the field along the axis of a charged ring. At first sight, it looks like this is a two-dimensional problem. At first sight. But in reality, it is not if we use a polar coordinate system, right? If we use a polar coordinate system for this ring distribution, this problem reduces to that of a one-dimensional problem. But qualitatively speaking, how does the field works along the axis of this ring? Okay, so here you go. We have the infinitesimal charge contribution here at this spot is contributing an electric field in this direction. Opposite to this charge, we have this other infinitesimal charge distribution right here that's contributing also an electric field like this one. Okay? Then we have the infinitesimal charge on the other 2 points, right? That's also contributing an electric field in this plane here. This plane is the XZ plane, whereas before the electric field here would be in the XY plane. The neat thing about this problem is that it's the easiest type of continuous charge distribution problem that you are going to see in your life. Okay? Why is that? Okay, the reason is very simple. The reason is because the distance of the infinitesimal charges to this point are going to be exactly the same. That's because we are talking about a problem that has a geometric, because of the geometry of the problem. Okay? There is a problem that has a geometric symmetry. Okay, if you were to calculate the electric field outside this axis, somewhere around here, then the distances from the infinitesimal charge distribution would be different. But along this axis, the distances are all the same. And because the distances are all the same, this problem is going to be easier to solve. So, going back to our ring illustration, right? We have those infinitesimal electric field contributions from those infinitesimal charged rings, and don't forget the ring is uniformly charged. That's why the electric field of this infinitesimal charge is equal to the electric field of this other infinitesimal charge. I mean, it's equal in terms of magnitude, right? Because the direction is different. And also, any infinitesimal ring, any infinitesimal charge in this ring here will have the same electric field contribution, the magnitude. And also the angle is going to be the same too, because the distance from here to here is going to be the same, the distance from here to here, okay? So here you go. Mathematically speaking, we can conclude that we are going to have an electric field along the x-axis only at that specific point, right? Going back here you go. The y field cancels, right? And here in this case, the field along the z direction will gonna cancel too, because this field here is gonna be in magnitude equal to the other one. This angle phi is gonna be the same angle as well for anywhere along the ring as we integrate, right? So the first conclusion that we obtain from this simple drawing is that the final electric field, the net electric field, is going to be an electric field, the x component of the electric field in the x direction. The y and z components are going to be 0. That's the first conclusion we get from this simple drawings, those simple drawings that we see right in here, okay? Whether is along the here too, right? Here we're going to have the same situation, okay? The angles are going to be the same, and so on, right? So, in the next step, we'll calculate this net electric field, the x component of the electric field, okay? Remember, the electric field has only a x direction. Here you go. The infinitesimal electric field, infinitesimal x component of the electric field, can be here written in terms of k dq r prime square. I am calling prime the distance from each infinitesimal field element times a cosine of theta, cosine of phi. Okay, so the projection of this field here is going to be the one that we should worry about. That's why I put the cosine of phi here. The r prime is going to be this distance from here to here, which is going to be equal the distance from here to here. Let's change it. Let's change the notation. R prime, right? Just to keep consistent with my notes there. Here you go. Okay. And we have to write this cosine of phi in terms of the variables that we have there in the drawing. Okay, cosine of phi, this angle phi here, is also equal to this angle here. And the cosine of phi is going to be this distance x from the center of the ring divided by r prime. Okay, so here we go. That's the drawing we have here for this angle. X over r prime is cosine of phi. Okay, and we try to continue solving this problem, right? We are going to have k dq over r prime cubed, because this r prime is combining with this r square. And what do we do next? We rewrite our r prime in terms of the radius of the ring and the position along the x-axis. This x here is not a variable, okay? It's not a, well, in this specific case, it's not a variable, okay? And now, what do? We need to integrate. But that's the important key for this problem, okay? Here you go, we have this dq that must be integrated. And as you know, the distance of each dq is always is the same in this case of the ring. So mathematically speaking, this is a simple problem to solve. X remains constant. You don't treat the x as a variable. Why you don't treat the x as a variable? Because we are integrating here in the ring. The distance x to the center remains the same, right? And what we are integrating, we're integrating over this ring right here. That's why the x can be taken out of the integral. Okay? And now we are left with the simple integral over the dq of the ring. There is no variable whatsoever there, integrating any integrating variable. What's x prime, y prime, or even r prime is not there, because r prime is a constant. When we take this integral, we get the net charge of the ring. That's Q, and we finally get this final result for the ring. Okay, that's the electric field of the ring, the net electric field of the ring. What we are going to do next is to rewrite the electric field, this electric field here, for the case in which the x distance is much larger than the radius of the ring. Okay? So, since x is much greater than r, we can neglect this r square. And let's see what we get, right? Now, notice that I put an approximation right in here. I made r approximately equal to 0 because x is much greater than r. And we have this relationship. And finally, look what we get. We get the case of a point charge, right? kqx squared in the x direction. Okay, so note, what's important to see here is that for very large distances from a charge, from a net charge, from non-zero net charge distribution, the E field varies with the inverse of the square of the distance. Okay. So that's how we solve the easiest type of problem for a continuous charge distribution. This one is the easiest one because each infinitesimal charge distribution is at the same distance from the point where we are trying to calculate the electric field. Okay? Now we're going to do another example, the sample of a uniform linear charge distribution. So this charge distribution is one of the ends of the charge distribution is a given distance from the origin of the axis. And I want to calculate, again, it's going to be a simple problem, right? We're going to calculate the electric field at this point at the origin. Okay? Note that this end here is at a distance a from the origin, and this other end here is a distance a plus L. So this charge, this rod, has a length L. Generically speaking, okay, this infinitesimal charge contribution is going to contribute an infinitesimal electric field dE1. Okay, this other dQ2 charge, also of length dx, is going to contribute a slightly larger field because it's closer to this point. I'll call dE2. Okay, so let's set up the problem mathematically, how it works, right? So here we go. The infinitesimal electric field is going to be given, is going to be given by, just like we wrote before, I'm going to write it here, it's going to be given by K dm. Okay, I'm going to write down R prime square. I am writing down R prime. What is R prime? R prime is the distance of the infinitesimal charge. In this case, R prime ends up being X prime, right? Is the distance from the infinitesimal charge to the point where we are trying to calculate the electric field. So I'm distinguishing the coordinates in the x, y, z volume without prime, and everything that within the electric charge distribution has a prime component. So that's very convenient to discern, right? To the coordinates related to the points along the rod and the coordinates in the whole space. We usually do that to solve this problem. So here you go. Using that technique that I mentioned to you before and that we used also in physics 37, right? We can here write my dm in terms of the charge density, the linear charge density. Let's here write that here below. dm over dx is going to be equal to lambda. Okay? It's going to be equal to lambda, which, by the way, lambda is uniform, right? It's going to be BQ divided by L. Remember, we're doing the uniform distribution problem. We're not doing a non-uniform distribution problem. In the case of non-uniform distribution problem, this lambda here would be variable along the length, would be a function of x prime, right? Along the length of the rod. So here you go. What do you do here is simple. Oh, by the way, I should write down dx prime, right? Because it is infinitesimal lengths along the rod. We can here write that as lambda dx prime, which becomes q over L dx prime. And now we can substitute what we see here, either this term or this term, right in here. And that's what I did, right? Lambda dx prime becomes q over L dx prime. And because the charge is positive, the r hat vector becomes minus x hat vector. Okay? So we sort out all the negative signs, minus k, q over L dx prime x prime square x hat. Okay, and now it's a question of integrating this result. And going back to our drawing, here you go, we should integrate from x prime equal to a all the way up to x prime equal to a plus L. Okay? That's what I did, x prime from a all the way up to a plus L. X hat is going to be a constant. KQL is going to be a constant as well, so they can be taken out of the integral. And we are left with the integral right here that can be easily calculated, right? Dx prime divided by x prime squared. Okay, this integral here is equal to that minus 1 divided by x prime. The minus 1 must be here because the power of x prime is minus 1. So when we differentiate to get what you see here, we have to put this negative sign. The limits are a to a, from a to a plus L. Okay. Apply the limits. This negative sign first cancel out with this negative sign. Let me emphasize that now we have a positive sign before we apply the limits. Right? And when you apply the limits, you get this result here. Can you do more than that? At this point, you can stop here, but I want to put this equation in a different format for a reason, okay? But in principle, that should be our final result. But if I want to put that under the same denominator, what do we get? Let's see if we can get something simpler, right? Here you go, I'm putting everything under the same denominator. This guy gets term A, and here A plus L with a negative sign, right? And then we combine those two numerators. The A cancel out with this minus A, and we end up with a minus L here, which, by the way, ends up being this result here. I'm going to here write it. Here you go. That's what's going to be the net field of that linear charge distribution. Did you notice that we have a problem that's a one-dimensional problem, but it was more difficult than the ring problem because the distances of each infinitesimal charge varied. The distance of each infinitesimal charge in the rod varied from the point at the origin that we are trying to calculate the electric field, right? And now we are going to do the same thing that we did before. Here you go. Let's say this is the exact solution for that point at the origin of that's the exact solution of the electric field for that point at the origin. Okay. Now what you're going to do? You're going to do that approximation again. We are going to find out what is the electric field for A much greater than L. Okay. And just like we saw before, this electric field must be reduced to that of a point charge. Okay, so let's see how it goes. Okay. Okay, so here you go. That's the exact solution. And we're going to do for A much greater than L, right? What's A much greater than L? Let me picture that here for you, what exactly means A much greater. That's what means A much greater than L, okay? This end here of the rod is at a distance that's much larger than this L, at least 10 times larger. That's how we pass a judgment about being much greater or much smaller, right? This is the case of A much greater than L. For A much greater than L, this rod here starts to behave as though it is a point charge. Okay? Remember, we are calculating the field here at the origin, right? And how do we do that? We try to rearrange this equation in such a way that we have a ratio that's much smaller than 1. We can put the A in evidence to do that, and that's what I did here. I put the A in evidence to do that. This A combines this other A to come up to become A squared. And since this term here is much less than 1, much less than this one here, we can make it, approximately equal to 0 and get this final result that you see here. Again, note, see, the A here in this case is doing the job of the R, right? The distance from the rod. Note, see that what we end up having here is the electric field of a point charge. Okay? I also put it approximately equal. Okay. So let us document everything that we have done so far, right? First thing is that the E field of point charges. Then we did the E field of a uniformly charged annular distribution, which is the simplest of the problem that we have a finite distribution of charges. The next one will be E field of a rod, of a finite rod. We did that. The next one that we are going to do, next in line, you go. Next in line is the E field of a uniformly charged ring. Okay, that's the one. In order to do that, we are going to use this result here of the ring. Here you go. Calculate the field of a disk of radius r, of a uniformly charged disk of radius r. The E field of a uniformly charged disk of radius r with a net charge q. At a point again along the x-axis. At a point along the axis, okay? It's better to put here the axis of the disk. The axis of the disk of this disk, which is, by the way, perpendicular to its plane. The center of the disk is located at the origin of the XYZ axis. How it looks like in a drawing? Let's see how it looks like in a drawing. It looks like that. Okay? So here is my disk, right? Which, by the way, is oriented in the same way that the ring was oriented, right? Remember how we did that? Here's the disk orientation. Here is the ring orientation. Okay? The difference now is that this whole plane that you see right here is uniformly charged. This is the case of a two-dimensional problem. But how do we solve this problem? Well, we solve this problem by visualizing my disk as though as it is made up of several rings of infinitesimal thickness. Okay? Here you go. Here's the case of one possible ring, and then we have other possible rings as well. And then we have to sum up the contribution of each of those rings. Okay? Each of those rings are going to have an electric field also parallel to the x-axis, along this axis, right? Again, remember, we're doing the electric field only along this axis. If you want to calculate the electric field outside this axis, it's a much difficult problem from the integration point of view, okay? So those fields add themselves, and then you end up only with the field along the x-axis. Here you go. Those uniformly charged rings, they are going to create a net electric field that's going to be along the x-axis because the field itself is spin like a cone. Okay, a cone that is going to have zero electric field along the y and z directions. Okay, go. So let's see how we solve this problem. That's just the quick qualitative treatment. As we did before, we recognize that the electric field is along only the x direction. Okay? And the infinitesimal electric field is going to be that of the ring itself. The dq in this specific case is going to be a dq that is a ring itself, right? Not just a little slice of the ring, but the ring itself is the dq in this case. Because we have a cosine of phi here, we can here write our cosine of phi. Here you go, here's the phi angle. And also should be a phi here. That's going to be x divided, and again I'm going to write that at r prime, which by the way is the distance of the infinitesimal ring to the point where we are calculating the field. Okay, x divided by r prime. But the r prime from the cosine combines with the r prime of the electric field, right? You end up having a cube. Recall that the r prime, which is this distance here, should be r prime squared should be equal to x squared plus big R squared. Big R squared. Oh, by the way, it's not big R squared. Sorry, big R is the radius of the disk, right? It's r lowercase r prime squared because we're dealing now with the radius of the ring, and this r prime is going to be variable. So I wrote that down. Let's see here. Yeah. Wait a minute. I'm gonna. Yeah, it should be big R prime to distinguish from the other lowercase r prime. Okay, we have big R as the radius of the disk and big R prime as the radius of the ring. Going back to our equation, yeah, we do have R prime here. Okay, R prime square plus x square is going to be equal to lowercase r prime square. Since the r prime, lowercase r prime, is raised to the cube, we have to have this 3.5 right here. And now we're coming to the point where we are going to integrate. The k and x are constants in this problem. Okay, x right here is not varying, and we can take it out from the integral. dq stays here, and now we use the value of the surface charge density, which is dq dA prime. Okay, dq ends up equal to sigma dA. Don't forget that sigma in this case is going to be what? It's going to be big Q over the area of the circle, which, by the way, is going to be pi r square, capital R square. We here write this Q, this sigma, as what we saw here before, and we can start integrating, right? I will substitute that here later on in this integral. So here you go, dq is sigma dA prime. Okay, dA prime means that we are integrating over the surface of the ring distribution, of the charge distribution. Sigma can be taken out of the integral as well. dA prime can be written as what? Here you go. That's my dA prime, right? My dA prime is like a rectangle. See here, see my ring here? My ring, we can cut it down and stretch it, right? This ring has a side dr prime and a length 2 pi r prime. So the area is going to be 2 pi r prime dr prime, right? And of course, don't forget, this should be capital R, not lowercase r, and capital R as well. So you don't mix up with this other r prime. Oh. Okay, don't forget this one is capital R prime. So we don't mix up with this r prime. And also this r prime here is different from this big R, because it's the radius of the ring, not the radius of the circle. Okay, 2 pi r prime dr prime. And now we have my integrating variable, which is this r prime. Now, each infinitesimal charge distribution changes as I integrate over this surface, right? So here you go. My lowercase r prime is changing as I integrate over this whole surface, this distance r prime. The x doesn't change in the process, right? The x doesn't change in the process. But the big R prime and the R prime are changing simultaneously. So sigma 2 pi can be taken out of the integral. Sigma is that value that I told you before. The pi is going to cancel out this pi, right? And look what we get, 2q r squared kx. And now you have to worry about this integral here. The limits are from 0 to the big R value. And this integral is easy to calculate, right? Because we have r squared here downstairs, and you have r prime squared downstairs and r prime upstairs, integrated over the r prime. Okay, so that's the integral what you saw here with the limits. The limit of r prime goes from 0 to big R. Okay, and apply the limits. We are applying the limits here. Big what this line is all about? This line here is just to confirm that the differential of this term that you see here with respect to r prime ends up being my integrand. That's what it's all about, okay? And indeed it is, right? r prime squared plus x squared raised to the minus 3/2 power. So when we apply those limits, we go to this line right here. Here for r prime equal to r, here's for r prime equal to 0. Square root, negative the square root. Okay, we get this value, we get this ratio as well. And that's our final electric field of the ring. And we go ahead and do the same exercise that we did before to find out if this guy, if you see right in here, reduces to that of a point charge, right? I have an illustration right in here. Okay, here you go. That's what x much greater than r is all about. Okay? That's how the radius, that's how the disk looks like when its radius is much smaller than the distance. Here in this illustration, now you see the disk without the infinitesimal ring. Okay, so as the distance becomes larger and larger, the disk starts to look like a point charge. So let's do the math. Okay, for r much smaller than x, there are two ways, right? The lazy way, like we have been doing before, just by putting the big R as 0. If we do that, you do not get the result that we want. We get the 0 result. Okay? If something like that happens, that's because we're doing something wrong. That's so-called the trivial solution. Okay? And then the one that's not the lazy way, we have to do the actual binomial series expansion. Okay? So I'm gonna get my square root here term. I'm gonna put the x in evidence to get a ratio here that's gonna be smaller than 1. Okay, and then do the binomial expansion. When this x squared goes out of the square root, we end up with this x. Okay, and I am rearranging my term that has the square root. 1 over x. That's another way of writing this ratio, right? And now we finally can here write this term here as an approximation using the binomial expansion. What's the binomial expansion? The binomial expansion is going to be given by this term 1 minus the power that we see here. The power here is minus half, right? That's why we have a minus half here. So if we, strictly speaking, right, this ratio that you see here is something like that. Oh, something like that. Okay. Minus half the power times this term here. And I put an approximation because we have other terms here that are going to end up being very small. We're going to have a r to the fourth power divided by x to the fourth power, right? Which is going to be even smaller than what you see here. And that's the approximation that we use. Here writing it in a different way, the ratio is going to be something like that. And now we can get a solution that's not a trivial one. Now we can get a solution that's not a trivial one. Here you go. Here's my electric field. I'm going to write it down. Here you go. The exact solution of my electric field. Apply this approximation to this term. Okay, and we get this term is this one right in here. Note see that what you see here, this guy here multiplied by minus 1 over x is going to cancel out this one. That's what we have. And we are left with this term, which again is that of a point charge distribution. 1 divided by the distance squared. So now we have our other problem that we solved for a uniform charge distribution. Let's add that. Here you go. Point charge distribution. E field of a uniformly charged annular distribution of a ring distribution. Annular / ring distribution. E field of a finite rod, and the field of a uniformly charged, not ring, uniformly charged disk. Okay? We have to correct there before. Disk. The next step now is to find out what would be the electric field, how the electric field would look like if the point that you are calculating is not too far away from the disk, but very close to the disk, like here, this spot, okay? In this specific case, the radius is much greater than x, calling this point here, position x, right? So, going back here, we did for r much less than x, which reduces to a point charge. But then we can do the opposite too. What if the point is very close to the charged surface? What if x is much less than r, or r is much greater than x? What type of solution do we get? Okay? So we start with the exact solution. That's the exact solution. And instead of factoring x, we're going to factor r to get a x over r ratio right in here. Okay? And that's what I'm going to do here. Here you go. In this case, not only I am factoring r here in this denominator, but I'm also distributing the x inside that term in there. When we do that, we get this x divided by x, which is 1, by the way, and then we get this ratio that you see right in here. Okay? Okay, so one quick way of finding out if the lazy solution works is by experimenting with x equal to 0, right? And see if you get the trivial solution or not. If you get the trivial solution, you have to go through the long route of experimenting with the binomial approximation. Okay, and so here you go. Because x canceled here with this x, we don't have to worry about making it equal to 0. But then by making it equal to 0 here and here, what do you get? We get a non-zero solution, which is 2kq over r squared. In this specific case, r squared is a constant, is the radius of the disk, right? K is constant, Q is constant, and R as well is a constant as well. So we get this interesting result that for positions x, for a position x very close to the surface of the disk, we get that the electric field is going to be a constant, a uniform electric field. Okay? And that's an important result here. Let me show you. So here you go. What does it mean? It means that we have this type of situation. When the charged surface is very large compared to the positions compared to the distances from the plate itself, the electric field is going to be uniform, just like you see right here, along the x direction. On the left side is going to be pointing in the other direction, right? Because this is a positive plate. Remember that electric fields, they start from the positive and they end in the negative. This type of result is very important, so much that we do experiments on that. Okay, here you go. Here's the case of a positively charged plate. A negatively charged plate, the fields behave just like that. It's still uniform, but it points towards the charge distribution. And if we put one positive plate next to a negative plate lined up just like that, what's going to happen? We can use the superposition principle of the electric field to recognize that the field from the positive plate points in the same direction as the field from the negative plate inside this volume. So they reinforce each other. However, outside the volume of the plates, the field of the positive charge points in opposite direction with respect to the field of the negative charge distribution. It happens both this side, to the left, and to the right. Okay, in this region. So you can see that the electric field is going to be approximately 0. We can, the correct way is to state that it's approximately 0. Whereas the field on the inside adds up, and we get this result here. Okay, where the field is concentrated on the inside. So that's how we generate a uniform electric field. We have uniform gravitational fields nearby the surface of the Earth, and nearby the surface of a charged disk, we also have a uniform electric field. If we combine with another plate of negative charge, you're going to have an electric field equal to 0 outside this volume. Okay? So, going back here, when we have two plates, one positive and the other negative, and the other negative next two charged plates, right? Two charged plates, one positive and the other negative next to each other, comma, the field between them becomes larger, twice as much. The field between and outside them becomes negligible, twice as much, or, right? For KQ, which by the way is equal to that. And the field outside them becomes negligible. Outside them becomes negligible. We can elaborate a little bit more on this result that you see here. Okay? How I'm going to rewrite this equation that you see in a different way. Okay? I'm going to multiply and divide this expression by pi. Pi and pi. Okay? Note that pi r square is nothing but the area of the plate. Okay, and now we have this term for pi k multiplied by this ratio, which by the way is going to be equal to the surface charge density sigma. Recall that this k that you see right in here can be rewritten in terms of the dielectric constant, right? Here you go. The dielectric constant epsilon naught. And what that's going to be? It's going to be 4 pi epsilon naught, the dielectric constant. Okay, the 4 and pi cancels each other, and you end up getting what? Sigma divided by epsilon naught. That's just another way of rewriting your electric field inside the volume of the two charged plates. Okay. So having told you that, right, what you see right in here is going to be what? It's going to be half what you got in the other one with two plates. So if for two plates, one positive or the other negative, you get sigma over epsilon naught. For a single plate, the field is going to be uniform as well, but it's going to be half the strength that you got there. The field outside the plates is outside the plate is negligible. Note that in this case we use the lazy way, but it's not always that we can use the lazy way to solve a problem, right? Sometimes you have to use the binomial approximation. Now I want to talk about the motion of an electric charge in a uniform electric field. Okay? So you can have here the uniform electric field can be generated by two plates of opposite signs, right? This volume here will generate a uniform electric field. From the equation for the electric force, you know that if the field is uniform, the force is going to be constant and uniform as well, right? Because the field is uniform, constant in space, the force applied will also be uniform or constant in time. So if we place, for instance, a positive charge next to the positive plate, this charge is free to move here in this space in between the two plates. This charge is going to feel a repulsive force to the left. And this force is going to be given by the charge times the field, which is approximately Q sigma over epsilon naught. Using Newton's second law, we can find what the acceleration of this charge of mass m, okay, is going to be, assuming that there's only an electric force, right? Assuming that there is only an electric force, the net force is QE, Q sigma over epsilon naught, mass times acceleration. Newton's second law also holds under this circumstance, and you can obtain the acceleration of this charge within that field. It's going to be something like that. Okay? Q over A is going to be the sigma, right, of the plates. So this charge is going to be linearly accelerated, right? Okay, here you go. Here you go. What if the charge is injected between the two plates? Okay. But before we go to the other one, I'm going to portray this problem that you see right in here in a different light. Okay. I am going to change the orientation of this problem. How do we do that? Here I change the orientation of the plate, of the two plates, so you can have a more familiar vision of what this problem would represent, right? So notice that the situation is analogous to that of a gravitational field nearby the Earth's surface, in which what you see here should be the acceleration of gravity, right? And an object that's subjected to the acceleration of gravity, which, by the way, has a constant force. That's analogous. That's the analogy that we have. Now, what I want to show you is what we get when the charge is not already within this volume, but we inject the charge with an initial velocity in this field. Okay? This situation would be analogous to that of a projectile motion. Why is that? Because the moment that this charge enters the electric field, it's going to feel a constant force towards the negative charge. And because the force is constant, just like in the case of the projectile motion, the electric charge will describe a parabolic motion within this volume. Okay? So those are two cases for an electric charge within subjected to a uniform electric field. That's what we have for this chapter on the electric field, which is chapter 22. Now we're going to start covering chapter 23, which is Gauss's law in the book. Okay, Gauss's law. What Gauss's law? Let's write that down here in the notes. Well, Gauss's law is nothing more than a different way to solve for the electric field in a rather easy fashion. Okay? At this point, so far I have shown you how to calculate the electric field using Coulomb's law. But there is another technique to calculate the electric field that we call the Gauss's law. The Gauss's law is just a different format of Coulomb's law. It's the integral format of the Coulomb's law. It's given by an equation like that. Here you go. This is one of the laws of electricity and magnetism. Just like Coulomb's law is one of the laws of electricity and magnetism, Gauss's law is the same law but in a different format, in an integral format. So I need you to memorize this equation, integral of E dot dA, and this integral is a double integral. Taking over a closed surface is going to be equal to the total charge inside the surface divided by epsilon naught. Okay? This term that you see here, that is the integral, it has a name. It's called the electric flux through an enclosed surface. Let's visualize what that is. Okay, so here you go. Here is a uniform electric field in space. And I have shown to you a surface that's not closed, but a surface that's opened. Okay? We can calculate the flux, electric flux through the surface by multiplying the value of the electric field by the area that we have right here. Okay? In this case, the electric flux is going to be just E times A. Because now what, here are the surface is, is perpendicular to the drawing, right? It's the same as this surface here, but under a different view. What if the surface is oriented 90 degrees parallel, the surface oriented parallel to the electric field lines? In this specific case, the vector area is going to be perpendicular to the electric field. Consequently, the electric flux is going to be 0. Okay? So here you go. I can write that down right in here. Electric flux is EA. EA. In this specific case, the electric field is traversing the surface, and due to the orientation of the surface, the vector area is parallel to the electric field, so consequently the electric flux is going to be EA. Okay? Notice that in the definition of the electric flux, we have a dot product right in here. Okay? So if the electric field is parallel to the area, the cosine of the angle between those two vectors is going to be 1. Okay. Similarly, if the surface is parallel to the electric field lines, the electric field line is just going to graze the surface. Right? The surface is parallel, but the vector area is going to be perpendicular. In this specific case, the electric flux is going to be 0 because the cosine of 90 degrees is going to be 0. Here is another example of a surface, imaginary surface, that makes an angle with the electric field. The area vector and the electric field vector let's say, makes an angle theta with each other. Consequently, the electric flux now can be written as EA cosine of theta, which is theta is the angle between A and the electric field. Okay, and by angle between them should be, you know, the angle that you get whenever the two vectors are placed tail to tail. That's the idea that I want you to have about the electric flux. But that's not Gauss's law yet. Gauss's law involves what? Gauss's law involves a closed surface. Okay? So let's see how a closed surface comes about to be, right? For the case of a point charge, okay, you can come up with this closed surface, which would be a sphere, an imaginary closed surface. If the sphere is centered at the charge, the electric field and the area vectors are going to be parallel to each other, right? And the electric flux is going to be the electric field at this point times the area vector times the area of this sphere in this specific case. Okay, if the surface is not centered at the charge, then the problem becomes more difficult to solve, because the angle between the area vector and the electric field are going to vary throughout this spherical surface. Okay, in the first case it's easier to get the electric flux. In this case here it's more difficult to find that out. Okay, so keep that in mind for Gauss's law. And what you need, again, what you need to memorize is this integral. Integral of E dot dA with respect to a closed surface. Q enclosed is going to be the charge inside the imaginary surface. Okay. In the case of our imaginary surface, like this one, the enclosed charge is going to be this positive charge, whatever value it has. Here too, you have the same thing. Okay. Here you go, charge Q, x-axis, y-axis. We already know that the electric field for a positive charge is away from the charge itself, right? So what we are going to do now, we are going, with this piece of information, we are going to derive Coulomb's law from Gauss's law. With the only piece of information that the electric field are the sources, the positive charges are the sources of the electric field. It means that it radiates away from the charge. Gauss's law is this funny type of law that requires a symmetry to solve some problems, okay? But it's still advantageous to use Gauss's law because it allows you to solve in a rather quickly way what would take some heavy integration, okay? So what are the key ingredients for Gauss's law? The key ingredients for Gauss's law is, first, to have a qualitative idea of the behavior of the electric field around your charge distribution. In this case of the point charge, it's going to be the electric field radiating away from the point charge. Since the point charge has a geometrical symmetry, okay, we can draw a Gaussian surface around this charge, and because of the symmetry of the point charge, this Gaussian surface that we're going to choose is going to be a sphere. A sphere around the point charge. Okay? In the case of this sphere has an area vector that points normal to the surface itself. Every sphere has an area vector that points normal to its surface, right? because also of the spherical geometry of the electric field, the area vector of the Gaussian surface is going to be parallel to the electric field as well. Keep that in mind. Here you go. Here is the area vector perpendicular to the tangent, to the surface tangent to the sphere. Okay, here is the radius of my Gaussian surface, centered at the middle of the charge. Radius r, lowercase r. Let's try to solve this problem using Gauss's law. Okay, point charge for the point charge. So what we're doing here is to derive Coulomb's law from Gauss's law, right? So with dot dA, first step, draw the electric field lines and approximate the electric field lines from your charge. For a single point charge, those electric field lines are going to be radial from the charge, right? The second step is to choose a Gaussian surface. This Gaussian surface is going to be a sphere, a spherical surface. This one that you see right in here. And by the way, because the spherical surface is centered at the charge, the area vector of the spherical surface is going to be parallel to the electric field lines. When we do something like that, what happens? The integrand inside the integral of the Gauss's law is going to end up becoming something like that. EdA times cosine of 0 degree, right? Which is, I'm going to do another step here, which is EdA. Because the distance at this point to the charge is the same as the distance of this point to the charge and so on, we can state that the magnitude of all those electric fields are going to be the same. So no matter what's the position of the electric field, its magnitude at the surface, at the spherical surface, is going to be the same no matter what, because the distance is the same from the point charge, right? For this reason, we can take this magnitude of the electric field outside the integral. And we are left with this integral of the area of the sphere. A sphere of radius r, remember that? The area of that sphere is going to be 4 pi r squared. The Q enclosed that you saw there is going to be just the big Q that we had with that factor epsilon naught. When we solve for the electric field, we get Coulomb's law for a point charge, just like we got before, KQ over r squared. This is a very simple example that we can use to illustrate Gauss's law and to verify Coulomb's law in terms of Gauss's law. In order to reach this result, I did not know the format of the electric field whatsoever. I knew only two things: how the electric field behaves in a qualitative way with respect to the point charge, right? That's how. I didn't use Coulomb's law at all. I derived Coulomb's law just with the knowledge of how the electric field behaves around a point charge. We can repeat that for a spherical charge distribution as well, of radius r and net charge q greater than 0. Now we will apply Gauss's law to a uniformly charged spherical shell. How does it look like? Well, my spherical shell looks just like that. Radius r and net charge q. Okay, radius r and net charge q. Here you go. The charges are distributed throughout a very thin layer of the shell. This layer can be considered negligible. Okay, so what do? Just like before, we see that we have spherical symmetry in this problem. Not only you have a sphere, but the charges are uniformly distributed as well. The amount of charge that you have here is the same amount that you have here. You don't have a higher concentration here and lower concentration there. No, that's not how it is. That's why it's called uniformly charged. So what do? we set the x and y axis, right? And we choose our Gaussian surface. We started for a radius less than the radius of the shell, less than r, big R. Okay? So how do we solve that? Here we go. For r less than big R, the enclosed charge is going to be 0. Consequently, the flux, the electric flux, is also going to be 0. The only way that this integral is going to be 0 is if the E is 0, because the area is not. Okay? So that's the solution, that's half of the solution. The other half of the solution has to do with values for R greater than big R. Here you go. Here is the spherical surface again, spherical Gaussian surface, an imaginary surface. Recall that this problem has spherical symmetry. Because it has a spherical symmetry, the electric fields point in the radial direction. Because it points in the radial direction, the area vector of this imaginary surface is going to be parallel to the electric field vector, just like in the case of the point charges, right? So if we solve that, here you go, we're going to solve this integral here. The Q enclosed is going to be Q. The integral is going to be, just like before, magnitude right? We no longer going to have the dot product here because the A is parallel to the dA. Just like before, we are going to have an electric magnitude of the electric field at this point is going to be the same as the magnitude at this point. And again, that's because of the symmetry of the problem. Okay? Consequently, the electric field can be taken out of the integral. The integral of the area is 4 pi squared. 4 pi r squared, where this lowercase r is greater than big R. And we do not need this term anymore. Right? And again, we get Coulomb's law, but only outside the sphere. Okay? Let's emphasize here. Here you go. We did the point charge. We did the uniform. We did the uniform spherical shell distribution. Right? Here you go. And we are going to do this other ones that you see right in here. Let's start with the uniform spherical distribution of charges. Net charge Q, and radius big R. Okay? Now we are going to do the case of a uniformly charged sphere. By uniformly charged means the sphere is solid and it has uniform charge from the center of the sphere all the way down to its surfaces. Here you go. Here is a three-dimensional sphere with a net charge Q, and all the charges are uniformly distributed from the center of the sphere to the surface, to its surface. Okay? The sphere has radius r, and we can put our x and y axis, and just like before, we should expect, due to the symmetry of the system, we should expect outwards electric fields. Electric fields that are outwards in the radial direction. If we do the solution for a Gaussian sphere, an imaginary Gaussian sphere of radius r that's outside the net charge, we get exactly what we saw for the spherical shell and the point charge. Okay, so here you go. For little r greater than big R, we have exactly what we had before. The electric field is going to be parallel to the area vector, and consequently we get rid of the dot product, and because the magnitude of the electric field over the Gaussian surface is the same, we're talking about the Gaussian surface, right? Don't forget this integral is being taken with respect to the Gaussian surface. It's not with respect to that imaginary Gaussian surface. That's why this integral is being computed over this surface here. We're not taking the integral over this surface in between or this other surface far away. Because we're taking this integral over the surface, the magnitude of the electric field here is the same as here, is the same as here, is the same as here. The magnitude, not the direction. Because of that, we can take out the electric field outside the integral. The process is exactly the same for the point charge and the spherical shell, as you can see. And we can find out that the electric field is kq over r squared. Okay? At r equal lowercase r equal to big R, that's the value that we end up getting for the electric field. We're gonna need that later on. Just hanging down. Let's just hang into this value here. What is difficult to do and is unique about this problem compared to the other one that we did is for the case where r is less than big R. Lowercase r is less than big R. Okay? So here you go. This Gaussian surface right in here. Here is the surface of the sphere. Here is the imaginary surface. That's what's different for this problem. But just like before, the vector area A is parallel to the electric field E. Okay? So at least in this regard, we can solve for this case just like we did before, right? I'm even gonna copy what we have here. Can even copy what we have here. What is different is the Q enclosed. What becomes different is the Q enclosed. The Q enclosed is no longer going to be big Q. It's going to be less than big Q. It's going to be less than big Q because the amount of charges inside this spherical Gaussian surface is less than the net amount of charges in the whole sphere. This value can be calculated rather easily. Okay? Q enclosed is going to be rho, which is the volumetric charge density, times the volume enclosed by the Gaussian surface. Okay? So, the charge density is going to be given by the net charge divided by the net volume of the sphere. And the volume enclosed by the surface of the sphere is going to be given by 4/3 of pi lowercase r cubed. Okay? Then we can do our simplifications. The simplifications come from here. This 4 pi, this 4/3 pi, here you go, and this other 4/3 pi. When you cancel them out, we get a relationship in terms of r cubed and lowercase r cubed and uppercase r cubed. So what we have is something like that. I'm going to simplify that so you can see the left side is going to be that integral that you saw before, and the right side is going to be that simple relation that you see right in here. Now the key is to find out what's the integral now. What's left is to find out what's the integral. Remember, it's the surface enclosed by the Gaussian surface. Okay? The imaginary Gaussian surface. The imaginary Gaussian surface has an area equal to 4 pi lowercase r squared. And now we can solve our problem in terms of the electric field according to this relation, right? And what do we get? We get that the electric field, oh, this r squared is going to cancel out this r cubed, right? We're going to get that the electric field is going to be a linear function of r. Note, see, just like before, that the magnitude of the electric field at the lowercase r equal to big R is going to be the same value that we got before, okay? Here you go. So there is continuity of the electric field at the surface of at the charged surface. Okay, note that we do have continuity of the E field at the surface of the charged sphere, but we do not have continuity on the derivative of the E field. That's typical behavior of electric fields. Okay, so we did all those examples: point charge, spherical shell, okay, and uniform spherical distribution of charges. What we have to do now are the infinitely long rod with the uniform charge distribution and an infinitely long cylinder of radius r. Let's do that. Infinitely long rod with a uniform charge distribution. The geometric figure looks just like that. It's a one-dimensional rod. It's very thin compared to the dimensions involved, and it's very long as well. Okay, the rod has a density that equal to lambda. Linear charge density equal to lambda is a uniform distribution. I have the x and y axis right in here. Right, and that's the x direction. The z direction is coming out of the plane of my computer. If you look along the x-axis, you see something like that, a line going towards you. Okay, and this line is very important for us to recognize that your rod has azimuthal symmetry. Not only has azimuthal symmetry, but it also has longitudinal symmetry because the charge distribution is uniform. Since the rod has azimuthal symmetry, we can come up with a Gaussian surface that is a cylindrical Gaussian surface. Cylindrical Gaussian surface of radius r, lowercase r. Okay, because of the symmetry of the system, we can easily see that the electric fields are radiating away from the rod. but it's not in the radial direction, but it's not in the radial direction in the sense of the spherical coordinate, but in the radial direction in the sense of the cylindrical coordinate. Okay, so that's how it looks like if we view the rod in the other direction, right? Along the radial direction, we see this electric field lines. Along the longitudinal direction, we see the electric fields in this way. Okay? The Gaussian surface that we have is going to be finite and smaller than the rod itself. Don't forget, it's a cylindrical Gaussian surface, okay, of radius lowercase r. And we can see that we have this cylindrical surface, this side surface. We have three surfaces, right? This cylindrical side surface, and you have those two caps at the end. One cylindrical surface and two planar surface capping the cylinder. Three different surfaces. The area vector of the cylindrical surface is parallel to the electric field, but the area vector of those two caps are perpendicular to the electric field. Here you go. Here, the cylindrical surface I call cylindrical surface number 1. The blue arrows are the area vectors. The cap on the right side I call the surface 2. The cap on the left side I call surface number 3. Okay. Here you go. Here's the area vector of surface 2 and 3, which are going to be perpendicular to my electric field as well. Okay, so I am calling the cylindrical surface of length L. Let's see how it turns out to be, how it turns to solve the problem in terms of the Gauss law, right? The Gauss law. Here you go. The Gauss law states that the electric flux through that imaginary Gaussian surface is E dot dA, and it's going to be equal to Q enclosed divided by epsilon naught. The Q enclosed is going to be my linear charge density times the length of the cylindrical surface, lambda L. So this integral can be broken down into three integrals, three surfaces, the three surfaces that you saw. The cylindrical surface, the lateral cylindrical surface, and the two caps, the two planar caps, the two discs, right, at the end of the cylinder, 2 and 3. It's still equal to lambda L. Okay. Because E along the third, because the E and A along the second and third surfaces is 0. Okay. Because of the angle between them, those two integrals cancel out, and we are left with a single electric field here in our solution. Just like before, the electric field, in this case the electric field is parallel to the A, consequently we get this solution right here. Because the distances of every point along here, the distances to the source is the same, the magnitude of electric field at all those points are going to be the same as well. And we can take the electric field outside the integral. Okay. And what else do we have to do? Okay, we have to get the area of that imaginary cylinder. The area of the imaginary cylinder is going to be the circumference of the cylinder times its length. 2 pi r L. The L cancel out with this L, so it's independent on the length of the cylinder. And we get a solution that's inversely proportional to the distance from the axis of the rod, 2k lambda over r. Don't forget, this is the result for an infinitely long rod, okay? That's why it's divided by r and not divided by r squared. If the rod were finite, we would be getting something different, okay? This result that you get is an approximation for a rod that's very long compared to the distance to the point where the electric field is being calculated. That's what's important to remember, okay? And that's spelled out right in here. So we are done for item number 4. Now we're going to do item number 5. It's a infinitely long cylinder of radius r. It's a solid cylinder of radius r. And uniform charge distribution, rho. Now the charge distribution is not going to be one-dimensional, but it's going to be a three-dimensional charge distribution. This problem is very similar to that problem of the sphere, of the solid sphere, okay? How does it look like in terms of the geometry? You have the cylindrical shell, right? And you have also the solid cylinder. I'm going to skip the cylindrical shell. So let's do the uniformly charged cylinder. Here you go. It's something like that. Side view of the cylinder is something like that, with uniform charge distribution. Here is the axial view of the cylinder. The situation is exactly the same for the rod, for the case in which we have the distance greater than the radius of the cylinder. Okay, so it's like that. You know, E dot dA, Q enclosed, epsilon naught. That's what we have whenever r is greater than r, okay? But I'm not doing that for r greater than r because the solution is exactly the same, you know, exactly the same for the rod. Okay, here you go. For lowercase r greater than r, comma, the solution is the same as for the 1D rod. 1D rod. Now, for r less than big R, the situation is going to be a little bit more difficult. You have E dot dA, Q enclosed divided by epsilon naught, and just like before, rho times V. And I'm going to say V enclosed by the Gaussian surface. The volume of the Gaussian surface is going to be pi r squared, the area of that cap of the cylinder, times the length of the Gaussian cylinder. This rho is going to be given by what? Since it's uniformly charged, rho is going to be given by Q divided by the volume of the cylinder, 4/3 pi r cubed. The cylinder has radius r. That's what my rho is all about. Okay, so E dot dA, just like before, can be broken down into three surfaces: the side surface of the cylinder and the two caps, which, by the way, is going to be the E dot dA, the flux through those caps, is going to be 0 because the field has radial behavior. What we are left with is this term, okay, which, just like before, can be taken out of the integral because the field is parallel to the vector area of the cylindrical surface. Okay. The area of the cylindrical surface is going to be 2 pi r times L. L cancels out, pi cancels out, and r cancels out. Note that we end up having a linear relation between the electric field. A linear relation for the electric field, right, of a solid cylinder. So that's what we have. And in summary, Gauss's law applies only to problems that have symmetry. We look at problems that has a spherical symmetry, such as the point charge distribution, the spherical charge distributions. It's not enough that you have a spherical geometry of your problem. It's not enough that you have cylindrical geometry of your problem. The charge distribution must also have this property. Okay? So, spherical symmetry and cylindrical symmetry. We did problems for infinitely linear charge distribution, infinite cylindrical charge distribution. And then we have to do for the infinite planar charge distribution as well. Let's do that together. That's another one that's important that we have to do. Okay? So the next problem again is for infinite charge planar surface. Infinitely charged planar surface with uniform charge density sigma. That's the illustration of the surface is like that. Okay, we already solved this problem using Coulomb's law, but now we are going to solve this problem using the Gaussian law, the Gauss law. Because this is a planar surface, we can do that little trick, right? Combining the electric field of infinitesimal charge distributions, and we can see that the electric field nearby this surface here is going to be approximately in the horizontal direction, right? So here you go. Here's the illustration. I'm going to draw the illustration without the Gaussian cylindrical surface. That's what we should expect for the electric field. Okay. The key here is to find out what would be the geometry, the symmetry of this problem, right? The symmetry of this problem that we are going to use is that of cylindrical as well. Why is that? Okay. So look here, if we draw a imaginary cylindrical surface, a Gaussian surface, right? What we are going to have? We are going to have area vectors here at the surface of the cylinder that's going to be perpendicular to the electric field. And then at those two caps, the area vector is going to be parallel. So compare this Gaussian surface with the Gaussian surface of the one-dimensional rod. Okay? In the case of the one-dimensional rod, the orientation of the cylinder is different, right? because the orientation of the cylinder is different, the electric field on the cylindrical surface is going to be parallel to the area and perpendicular to the area vector at the caps of the cylinder. So that's the important difference between the planar surface and the one-dimensional rod. The fields, the electric flux, in the previous one, the electric flux cancel at the caps, whereas in this one, the electric flux cancel at the cylindrical surface. If we look from the axis of the imaginary cylinder, it's going to be something like that. Here's the planar surface, right? Full of electric charges with a charge density sigma, uniform charge density sigma. And here's the imaginary Gaussian surface. It's a cylinder that protrudes from this charged surface. The cylinder has a radius r. You need that as well. Now we have to figure out. So there will be three surfaces. Going back here. Just like before, there will be three surfaces. Surface 1, 2, and 3, right? Here you go. E dot dA is surface 1, 2, and 3. The Q enclosed in this term is going to be sigma, which is uniform charge density, times the area of the Gaussian surface. The area of the Gaussian surface that I'm talking about is this area right here, pi r squared. So the integral can be broken down into three open surfaces. The area is pi lowercase r squared. The third integral of the third surface is going to be 0 because this dot product is going to be 0. And we are left with this integral. One integral is going to be for the electric field 1. The other integral is going to be electric field 2. Okay. The area that you see here is going to be pi r squared because the area of a disk over that charged surface. We have pi r squared. The r squared cancel out with this other r squared. That's why we get sigma over epsilon naught. And now we have those two terms that we don't quite know what their values are. E1 is for the electric field on one side of the surface. E2 is the electric field on the other side of the surface. Right? Here you go. Here you go. E1 is this field here. E2 is this field here. How do we distinguish them from each other, okay? Well, we do the following. There's this little trick. If we choose the distance of this cap to the charged plate the same at this distance of this cap to the charged plate, we can state in a very reasonable fashion that the magnitude here must be the same as the magnitude here because the distance to the sources are the same. That's the key realization that we must have to solve this problem. If E1 is equal to E2, then E1 plus E2 is going to be twice the electric field, and we end up with this solution, which, by the way, is exactly the solution that we got previously. Right? If you recall our previous solution using the disk that is very large compared to the distance, we got sigma divided by 2 epsilon naught. Okay, when r is much greater than x, we got this relation here, which ends up being the same. So we solved the same problem using two different techniques, and we got the same result. Okay? So now we are done with the examples of Gauss's law. As I mentioned before, We have problems that involve spherical symmetry and cylindrical symmetry. The problems that involve spherical symmetry are point charges and spherical charge distributions. The problems that involve cylindrical symmetries are linear charge distribution, cylindrical charge distribution, and infinite planar charge distribution. What are the steps to solve problems using Gauss's law? First, you have to identify if the problem has symmetry, either cylindrical or spherical. Come up with qualitative behavior of the electric field, just like we did. If the surface is positively charged, the field is going to point away from the charge. If the surface is negatively charged, the field is going to point towards the charge. Surround the charge distribution with an imaginary closed surface. Remember, Gauss's law deals with a closed surface. The closed surface is called the Gaussian surface, either spherical or cylindrical. The electric field will be either parallel or perpendicular to the area vector of the surfaces. Solve the integral for the flux, which will depend on the unknown field. In those problems that we did, the electric field is usually constant over the surface, so it can be taken out of the integral. Solve the right side of the equation, okay? So for the charge enclosed by the Gaussian surface, the Q enclosed, which is the right side of Gauss's law, and then determine the E field. So that's what we have for this chapter. And if you have any questions, let me know through email or during my office hours, okay? So thank you for your attention, and I hope to see you during my office hours. Bye-bye.